All right. Okay, so we are beginning a new unit, and this new unit is actually going to span over Christmas break. So we are going to be doing a deep dive on this quadratic family of functions. And Nessa, there's going to be quite a bit to this. And in the end, you're going to end up doing a project on quadratics that are going to cover all of what we talk about between now and, what we finish up in January. Okay. So if you didn't have it on the radar, how close we are to getting out, let me put it on the radar for you. We got 2 weeks until Thanksgiving break. We also have 2 weeks until all reassessments on quizzes 1 through 4 are closed. Okay? So make sure, quiz 5 is going to be after Thanksgiving break. No, we just took 5. Okay. The one on formative was 5. Yeah, you should have 1 through 4 in your possession. Okay? And those corrections must be completed by next Friday. Okay, not this coming Friday, the Friday following, the 22nd. Okay? When we come back from that break, we're going to essentially have 2 weeks, but on the Friday of the second week, we begin final exams. So there'll be at least one block period where we study, which means we're only going to have 1 week back from Thanksgiving break, and I'll most likely be assessing you on the things that we do in the next 4 lessons. Okay? So when we come back from Thanksgiving break on the Monday, we'll have like a review day. I'm not sure if we'll have the quiz on the very first one. I'll be letting you know. It'll either be on the first block or the second block. Just kind of depends on what we get through. Okay? So the first part of this quadratics unit, we're going to have an assessment on before we head into final exams. Okay? So you have one more test, if you will, coming before final exams. Okay? And then we'll finish up the quadratics unit when we come back from Christmas break, and then that's when you guys will work on your project for that as we begin the next new unit. Okay? So there's a lot going on with what we're learning here, okay? Because we're going to go deep down inside, and it's going to be all about relationships. Now, some of the things that you'll see, you've seen before, either in another class or I've already taught these things to you. However, the goal of this unit is not just to learn the individual things, but actually to understand how they tie together in one cohesive picture, because that's what your project is going to be on. Your project is going to be you showing me your thorough understanding of all of the components of quadratic functions and how they tie together cohesively in one big unit, or like I like to call it, one big family. So today we're going to start with the intro to the quadratics family and something that's called vertex form, which again, you've kind of already seen. All right. So I wanted to start with this here. And again, this is stuff that we've kind of already gone over, but I also want to put a little extra vocabulary to this that you're going to need and be able to use on a regular basis. So let's just kind of add to our notes here just a little bit, right? So a quadratic equation, I'm going to underline that, which we also could call a function, and that's really the more appropriate language that we're going to use, okay, is an equation to the second degree. This is going to become a very important word for us, which essentially means the second power, because as we get further along into our polynomials, we're going to start structuring our polynomial functions by degree, okay? And so it has one that has a variable that's squared. And so this is what happens with this quadratic family, okay? Now the parent function for this is what you see here, and we could say, or f of x is equal to x squared, right? Those are the same things. And so being able to bounce interchangeably between the y and the x, or the f of x, and x is obviously important for us. And then we've seen this parent function already, right? So if we take a value, we plug it in, and we square it, then we're going to get out a positive value. Now, I'll just tell you right now, in looking at some of the tests, when I asked you to evaluate the quadratic function, the biggest mistake made was that you didn't take into account putting the parentheses first and then plugging in your negative. Because when it's negative x squared and your x is negative, you got to go negative times negative is positive, and then the opposite of a positive is a negative. And so it ends up being negative. It's almost 3 negatives in a row, okay? But a lot of you didn't do that. You just didn't write the parentheses, and so then you just ended up with a positive of your variable, and that got you to the wrong answer on your evaluation. I saw that a lot. It was almost 50-50 in both classes. It was, if you wrote the parentheses down, then you almost everybody who wrote the parentheses down in their work got that question right, and almost everybody who did not write the open parentheses down and plug in the number got that question wrong. Just kind of as, cursory glance. So keep that in mind as we're evaluating functions. Okay, so again, in this case, right, if we take a -3 and we plug it in, we're going to get -3 squared, right? Which means -3 times -3, that's going to give us that +9, that +4, that +1. Of course, you put a 0 in and square it, you're going to get 0. And then if we put positive numbers in, obviously that's going to be easy here. Now, I'm going to use this language a lot, so I just wanted to kind of highlight this. You can box it, highlight it, however you want to indicate this. But this is something that I'll refer to as the parent function pattern for quadratics, the parent function pattern. And I've already used some of this language with you when we were looking at the different parent function patterns, right? So this parent function pattern, you're going to hear me say it's the 1, 1, 2, 4, 3, 9 parent function pattern, like that. And that's from the vertex. Wherever we shift the vertex to, like we saw with our transformed functions, right? Wherever that vertex ended up, then it was 1, 1, 2, 4, 3, 9, as long as it wasn't stretched or compressed, right? Some questions about that came up, like stretching is where we take that and we narrow it up. We pull those y values up by multiplying by a number greater than 1. And compressing is when we push it out flat, where we multiply by that fractional value of a. And so we push that down, okay? But we'll get to that in just a minute. All right, so then let's get it to sort of a picture of our graph here, right? So it's going to start at 0, 0. That's our vertex right now, okay? And then we're going to go like we did in our parent function lesson. We went 1 here, and then we went 1 here. And so it was 1, 1, and then we would put a point there, and then it would be 1, 2, and then 1, 2, 3, 4, right? And so the idea is that we follow this parent pattern from our vertex. So it's 1, 1, 2, 4, and then we can do 3, 9. So it's 1, 2, 3, and then we go up 1, 2, 3, 4, 5, 6, 7, 8, 9, like that. And so 1, 1, 2, 4, 3, 9. And then the same thing happens on the other side, obviously, because we're squaring these negative numbers. So we go 1 to the left and 1 up. We go 2 to the left and 4 up. We go 3 to the left and we go 9 up. And that gives us this smooth curved shape that we talked about that comes down here and then turns at that point and then continues on upward and outward. Okay? Now, this particular shape you can see here is called a parabola. It's an important word for you to know. That's the name of this curve. Okay? And this parabola has a equal fold line on it. And that equal fold line is called the axis of symmetry. Okay? And I'm going to refer to that often as AOS. So abbreviate that, axis of symmetry. And what that is again, it's that line with which we can fold the shape over on top of itself. It creates an equal distance from that line. And this axis of symmetry is always going to be a vertical line. So in this case, because I have this big dash down here, I'm going to put some little dash marks in red down this y-axis like this. And so this is our axis of symmetry. This is our fold line. And what we're saying by that is what we mean is that every point along this graph, wherever we choose to pick, is going to be the same distance on one side of the axis of symmetry as it is on the other side of the axis of symmetry. Okay? So the idea is that at the same height level, those points along the graph have an equal or a congruent distance back to that axis of symmetry. Okay? Everybody good so far? All right, so you can see here that it's going to cut this parabola into 2 equal halves. Okay, now what is the equation for the axis of symmetry that I just drew here? Anybody want to take a shot at what they think the equation for the axis of symmetry is? Anyone? It is x equals 0. Good job, right? Right? Okay, so let's remind ourselves of something here just real quick. Okay, let's remind ourselves that horizontal lines are always going to have y equals, and vertical lines are always going to be written in the equation x equals. So our axis of symmetry for this parabola above is going to be x equals 0. You're going to have to be able to identify the axis of symmetry. Okay. Now the axis of symmetry for parabolas is always going to be a vertical line because we're never going to have a parabola that looks like this. Okay, that's actually a hyperbola, and that's a totally different math function, or a totally different, math relation, right? Yeah, exactly, because this type of a shape would not be a function because, and some of you didn't read those like shuffling and order things correctly, and you put, oh, the vertical line doesn't hit the graph more than one time, but it was phrased in the negative. So you got to read those very carefully because I said, like, you're checking the ones for what was a function, right? And one of the distractor questions was a vertical line hits the graph more than one time. That is not a function if it hits the graph more than one time, okay? I saw people select that because they just saw vertical line hit graph, and you went through it too quickly. Got to make sure on reading questions like that, as we're moving forward, you take the time to clearly read through those questions, okay? All right, so our axis of symmetry is always going to be a vertical line because we're going to have this parabola looking shape here. Now, these can open up, right? Or they can open down. We've already seen this, okay? And so when we have that, this vertex, which is our turning point, right? This point where the graph either turns back up or turns back down, okay? That is always going to sit on our axis of symmetry. Okay, now if I want you to think about that for a second, right? If the equation for the axis of symmetry is x equals 0 in this case, then what that means is that one of the coordinates in the vertex is 0. The x coordinate in the vertex is 0. Okay, and so as we continue to expand this out, you're going to be able to see how that relates for you to be able to find pieces of information. Okay, now there's a couple of other pieces of vocabulary that we want to add on to this. So let's underline this word vertex, and then I want you to swoop an arrow like that. And we're going to say that the vertex will be what we call a minimum if the parabola opens up. So we'll classify the vertex as being a minimum, the lowest point on the graph, if the parabola opens up. It's the minimum. It's the lowest point on the graph, okay? And likewise, we'll swoop another arrow here. That vertex will be a maximum if your parabola opens down. Okay, so in this case, the vertex for the parent function is going to be 0, 0, and it's going to be a minimum because the graph opens up. Is everybody good with that? Okay, so language that you need to be familiar with so that we can talk effectively about this. The vertex, the axis of symmetry, what that means in terms of the distance from each point on the side of the graph. Okay, you need to be familiar with how to write horizontal and vertical line equations. You need to be familiar with the language of minimum and maximum, opening up, opening down. Okay, got to be familiar with all that language. Everybody good so far? Okay, cool. So just establishing some groundwork.
For the axis of symmetry, it's wherever the vertex is on the x.
So wherever that vertex is, right, wherever that shifts, up or down, right, it's going to be the axis of symmetry is always going to go through the vertex. So that x value of that vertex, that left and right value, is always going to match this right here, okay? And then we'll have some more specific notes for that as we move forward. All right. This is what you're going to need a nice sharp pencil for, okay? You're going to want to take good care of this paper. There are a ton of details for your project down the road that you will have on this paper. Everything you need to do your project will eventually end up on this paper. Now, you're going to want to be a neat writer. Please don't be a not neat writer for this particular document because, like I said, there's going to be a ton of information that you need to know. All right. So, this is what I like to call my quadratic family flowchart. This is my quadratic family flowchart. And in the quadratic family, we're going to be looking at 3 different formats of quadratic functions, and each one has its benefits and hang-ups. And I'm going to expect you to know the benefits and the hang-ups for each one of these and be able to use them accordingly for doing certain things. And you're going to show me in your project that you understand how all of these things are related. So you can see here that we have these 3 formats we're going to use. There's vertex form, there's standard and general form, and then there's intercept form. Okay, so let's just start with jotting down vertex form. And what we're going to do is we're going to write 2 functions in here. So we're going to write the first one here, and we're going to write the second one here. So just for your spacing purposes. So the first function that we're going to write down here in vertex form is going to look like this. We're going to say f of x is equal to a parentheses x minus h close parentheses squared plus k. That should look familiar.
Oh.
What is that?
Quadratic. Transform quadratic.
Thank you, Luch. That's exactly right. That's the transformed quadratic function. Okay? So we're going to have that format. Then we're going to have our standard or general format, which is going to look like this. And again, we're going to write 2 functions in here. So this one is going to be f of x is equal to ax squared plus bx plus c. This is our standard or general form of the quadratic function. And then our intercept form of our quadratic function is going to look like this. F of x is equal to a times x minus p group times x minus q group. Okay, this is our intercept form of our quadratic function. So I'm just going to give you a quadratic function in vertex form. So the one that we're going to work with here is f of x is equal to x minus 2 group squared minus 16. Okay, so first thing, I would like for you to write a equals, h equals, and k equals, and I want you to fill in those pieces of information right there, a, h, and k, from the actual quadratic function that I gave you. You should have put a is 1, h is positive 2, and k is negative 16, right? Because again, in our structure here of our generic format, it's always x minus, right? And so it's x minus h. So if I blocked in that h there and I blocked in that h there, we can see that that's positive 2. Where h would be negative, this would be reflective of a plus, right? Because that came from minus a negative number. We saw that with our transformations. Everybody good with that so far? Okay. All right. So the next thing that we need to do is we need to talk about some of the aspects that are beneficial for us in vertex form. Why do we use vertex form? Okay, and so give me just a second because I'm going to copy and we'll start with copying this down and then we'll talk about it in just a second. Okay, let's start talking about this a little bit, just sort of break it down. So I'm going to kind of zoom out here so we can see our example function down here, right? So when we talk about our vertex, right, our vertex for our graph should be easy to find. If we can identify the h and the k, like we did right here, then we know what our vertex is, because in this case, we know that h is positive 2, and that means our graph shifted to the right 2, and then it shifted down 16. And so that would put the vertex at 2, negative 16. So by finding the h and the k, you can automatically find the vertex. Now, we talked just a few minutes ago about stretching and compressing, and that is controlled by the a value, right? If a is greater than 1, then it's going to stretch like this, right? And if it's between 0 and 1, it's going to compress out flat. And then the opposite of that works when your parabola opens down, okay? So if it's smaller than negative 1, negative 2, negative 3, negative 7, negative 288 million, then it's going to stretch down. And if it's in between negative 1 and 0, that's where it's going to compress out like this, only facing down. Okay, everybody good with that? All right. Whether you have a maximum or minimum is going to determine whether or not you have a positive A or a negative A. If you have a positive A, then your graph is going to be opening up like this, which means you're going to have a minimum. If you have a negative A, that's your reflection over that horizontal line, right? So in this particular case, if we had just put a negative 1 in front of this, what is the equation of the line that it would have reflected over? Does anyone want to take a shot at that? Let's just say I took that function and I put a negative 1 out in front of it. What would be the equation of the line that that parabola went from this to this? That's sort of dramatic here. I should have probably just gone this to that right there, because there's a line that is reflecting over. Y equals what?
0.
No. Good try. If it were the parent function, it would be y equals 0, which is good because it's a horizontal line, right? How about this function, though? It's y equals negative 16 because the vertex shifted to down 16 and then reflected. See how that works? Okay? So then the reflection is always going to happen at the line y equals k. Did you catch that? All right. One cluck for yes. Okay. Now, we talked about, Lucy, you were saying like that x value, that axis of symmetry, right, is always there. So really how we're going to write our axis of symmetry here is x equals h. Because whatever h is, that's going to be the vertical line that goes through the first coordinate of our vertex that's going to give us our axis of symmetry. And then, of course, we're talking about our domain and range. In inequality notation is going to look like that. In set notation is going to look like this, right? And then for our maximum and our minimum, right, when we're talking about our range, right, if we have a maximum, our negative infinity, right, the downside is going to come up to whatever that k value is, that point where it reflected over, okay? And then the same thing with our minimum, then it's going to be positive infinity. Now, one of the things I noticed a lot of mistakes on when it came to doing domain and range on the last test was you didn't put the lowest value first. We talked about that. The lowest value always goes on the left. So I saw students who put negative infinity on the right. Can't have negative infinity on the right. It's got to be on the left. So if you got that order backwards, then that was an error that showed up. And I saw that pretty regularly. Okay? And of course, in these examples here, k would be a value, right? So like for this particular function, right? This here, would this one be a maximum or a minimum? Would this vertex be a maximum or a minimum for this function? Opens positive A, opens up, going to be a minimum, right? So then what would the range, how would we write the range for this one in set notation? Tell your neighbor how you'd write the range for this one, for this given function in set notation.
Bracket.
So range for this one should have been bracket negative 16 comma positive infinity parenthesis.
That's what I got.
Yeah? Okay, did you catch that? Why it's that way? Because it's a minimum, right? So that's going to fall into this pattern right here, where k is a number. Now, it's always going to be included in these parabolas, right? The only way that it wouldn't ever be included is if you saw something that like looked like this. But you're never going to see that because the vertex will always be included in our parabolas, in our functions, okay? And so in that case, we'll always have that included number. Okay. So a lot of things to write down, but again, not really anything super new other than maybe, plugging in a couple of these H and K letters in places that we haven't talked about, like axis of symmetry or maximum or minimum. Yeah? Everybody good? Okay. So the transformed version of this is what we call vertex form. And the reason why is because the vertex stands out very clearly to find. Everybody good? All right then. Okay, so let's talk about then, how do we go from vertex form to standard form? Because it's not just another form, it's mathematically connected, right? And that's part of the whole idea of what we're doing here is to find these mathematical connections and know them. And so to do that, we are going to simplify the input side of our function. We're going to simplify the input side of our function. Now, if you would have had me for Algebra 1, I would have given you my Farkified definition for simplify, which is do math until you can't do any more math. Simplify. Do math until you can't do any more math. So that's what we're going to do. We're going to take our function and we're going to do math until we can't do any more math on the input side of the function. But here's what I want you to do, just for sake of making sure that we can all do what we need to do. Let's put a little squiggle right here. And then let's write our vertex form of our function here. And then why don't you come up with the next line? You were going to do math until you can't do any more math on the input side of the function. All right, go ahead. Simplifying the input side or the right side of our function should have looked like that. So I'll zoom in a little bit for you here. So PEMDAS, right? We got to do our parentheses first. Okay. Can't do any math inside the parentheses. So then what comes next after parentheses? No. Exponents, which means we need to take x minus 2 group and multiply it by itself, right? That means x minus 2 group times x minus 2 group. Now, the way I like to do that is I like to use an area model like this up here. So I write my x minus 2 group on one side, my x minus 2 group on another side. I make the same number of boxes that I have for terms on top and bottom. And then I just find the area of each of these squares. So in this case, it would be by height and my length. So x times x is x squared. And then x times negative 2 is negative 2x. And then negative 2 times x length is negative 2x. And then negative 2 times negative 2 is positive 4. And then combine my like terms, because I have both x to the first power there, and I end up with this becoming this. Everybody good there? Okay. Are we done? No, because we can still do more math, right? What more math can we do? Yeah, so we can combine some like terms, right? Good. So then that's going to give us f of x is equal to x squared minus 4x, and then what's minus 12? Okay. Are we done now?
Oh, yeah.
Well, x squared, right, is not a like term with x, right? If we had a shipping company, we had a shipping dock, and we had boxes that were labeled x could go in one pile. Boxes that were labeled x squared would go in a separate pile. So they're not like terms, and the 12s don't have any x's on them. They just have numbers. So those would be like terms. So yeah, we're done. We've done all the math we can do on the input side. And so our standard form of this function is going to be f of x is equal to x squared minus 4x minus 12. Okay, you ready? Watch up here on the screen. 3/6, 4/8. 5/10, 7/14. 9/18, 25/50. What am I doing?
Same thing.
They're the same thing, but they look different. Just like unsimplified fractions are the same thing, they just look different. These two functions are identical. In fact, if we took them and typed them into Desmos, we typed this into Desmos here, and we typed this into Desmos here, we would get the exact same graph sitting right on top of each other as what kind of a system? What kind of a system? What kind of a quadratic system if they were sitting right on top of each other?
Independent.
What? No, not independent. Dependent consistent. Right? Because they would share every point in common. Because they're exactly the same. Okay? So if I set those two into a system of equations, it would be a dependent consistent system, which has how many solutions in common? An infinite number of solutions. Okay, so vertex form and standard form. If you want to go from vertex form to standard form, all you got to do is simplify the input side of your vertex form. Make sense? Okay. That's all we're going to do for today. We're just going to practice a little simplifying our vertex side. I don't want to overwhelm you with too much stuff because the next one gets a little thick. So we'll start with this. Okay? So let me point out one thing real quick. Actually, let me point out one thing real quick in this math problem. Okay, you watching? Okay. Let's say that you had an A of 2 in this math problem. Okay? Where would that come into play in terms of the simplifying? Would you deal with that on the first level, the second level, or the third level? So if you dealt with it on the first level, if you distributed it, what math are you doing when you distribute?
Multiplication.
Can you do multiplication before exponents?
No.
So if you have an A, you still need to simplify your exponents first. Then, let's say you had an A here. So now you'd have A here, and this would be in parentheses, right? Then you would distribute the 2 before you combine the positive 4 and negative 16, because you'd have to do your multiplication before your addition and subtraction. Does that make sense? Because some of these are going to have A's on it. Okay? All right. All right, so you go. Sweet. Can you do your work for you? What's going on here?
Yeah.
You know, I have the whole thing completely schematic.
Oh, how about
Nice. That's big. She's like, oh, I walked out Caesar Thomas Street because that's the Dodger sky.
Okay, so for each of these, I'm going to expect to see work that looks like this. Now look, hang on. Hold on. The expectation is that you should be able to multiply these by this point in your math career. Okay? If you need to do this, do it off to the side. That's scratch work. Okay? All right, that's scratch work. But this is what the work should look like on your paper. Does that make sense? Everybody got that? Yeah? Okay. All right, good. Okay. You're working.